From a previous lesson in calculus, we know that the dot product of two vectors can be expressed in terms of the magnitudes of the given vectors and the cosine of the angle between them. So, for instance, if the vector is grad f and another vector given is u, and let's say theta is the angle between them, then the dot product of grad f and u is equal to magnitude of grad f times magnitude of u times cosine theta. And since this dot product is equal to the directional derivative, then we now have another formula for the directional derivative, which is given by magnitude of grad f times cosine of the angle between grad f and the unit vector. So what can we conclude about this new formula for the directional derivative? So we can see that the directional derivative is maximum whenever cosine theta is maximum, and that is whenever cosine theta is 1. And the value of the maximum directional derivative is simply the magnitude of the gradient of f. On the other hand, the value of the directional derivative is minimum when cosine theta is minimum. So that is, cosine theta is -1. In this case, the directional derivative is equal to the negative of the magnitude of the gradient of f. A very important fact about the gradient is that it identifies the direction of maximum rate of change and the minimum rate of change of f at the point of interest. So if you get the magnitude of the gradient, then that value, that scalar, will be the maximum rate of change of f. And the negative of that value, or negative magnitude of the gradient of f, will be the minimum rate of change of f at the point of interest. Now, the gradient itself is the direction of the maximum rate of change, and the negative of the gradient is the direction of the minimum rate of change. We have the following. The rate of change is maximum whenever the value of cosine theta is 1. That is, when theta is 0, or the angle between u and the gradient is 0. So this happens when the gradient and u point in the same direction. In this case, the maximum value of the directional derivative is equal to the magnitude of the gradient of f. And this happens in the direction v1, where v1 is equal to the gradient of f at xyz. On the other hand, the rate of change is minimum whenever the cosine of the angle theta is -1. That is, when theta is pi and the gradient grad f and unit vector point in opposite directions. In this case, the minimum value of the directional derivative is negative of the magnitude of the gradient of f, and the direction of minimum directional derivative, we say, is equal to v2, where v2 is negative of the gradient of f. Let's try doing this example. So, given f of xy equal to y over x plus ln 2x minus y, let's find the maximum rate of change or maximum directional derivative of f at 1, -1, and give a vector along which it occurs. So by the previous discussion, the maximum rate of change of f at the point 1, -1 is just the magnitude of the gradient of f at 1, -1. And this occurs along the direction of the magnitude of the gradient itself at 1, -1. So let's compute for the gradient at any point xy. So grad f is partial of f with respect to x, comma, partial of f with respect to y. And these are easy to compute. So partial of f with respect to x is -y over x squared. Partial of plus 1 over 2x minus y times 2. Partial of f with respect to y is 1 over x minus 1 over 2x minus y. And at the point 1, -1, you can see that this is just the vector 5/3, comma 2/3. Now, let's compute for the magnitude of this constant vector. The magnitude is square root of 5/3 squared plus 2/3 squared, which is equal to square root of 29 over 3. And this number is the maximum rate of change of f at 1, -1. And the direction of the maximum rate of change is equal to the vector grad f at 1, -1, which is 5/3, 2/3. Now let's do this three-dimensional example. So let's say we want to find the minimum directional derivative of f equal to xy squared minus x squared z plus y cubed minus 1 at the point 3, 0, -2. So by our discussion, the minimum directional derivative is just the negative of the magnitude of the gradient of f at the point 3, 0, -2. So as usual, we solve for the gradient of f at any point x, y, z. And this is just y squared minus 2xz for the first component, 2xy plus dy squared for the second component, and negative x squared for the third component. At the point 3, 0, -2, this vector is 12, 0, 12, comma 0, 9, minus 9. And so the minimum directional derivative at 3, 0, -2 must be the negative of the above vector, which is negative of the magnitude of the above vector, which is negative square root of 12 squared plus 0 squared plus 9 squared, which is equal to -15. Okay. Another interesting thing about the gradient is that it is a vector normal to a surface at the point of interest. So in particular, if the equation of the surface is of the form f of xyz equals k, where k is a constant, then grad f at x naught, y naught, z naught is normal to S at the point x naught, y naught, z naught, where S here is the surface. So the tangent plane to S at P, if we recall, is just the plane to P that is that shares the same normal with S at P. And the normal line to S at P is the line through P that is parallel to a normal vector to S at the point P. The previous result about the gradient is very easy to prove, so let's see the proof. So given the surface S, whose equation is f of xyz equals k, and a point P on S. Now let's consider a curve passing through P and which lies on S. Then for any t, the value of f at this curve must be equal to k, since the curve C is on the surface S. Now differentiating this equation with respect to t, we get that partial f with respect to x times x prime of t plus partial f with respect to y times y prime of t plus partial f with respect to c times c prime of t must be 0, since the right side of this equation is 0. Or equivalently, the gradient of f, if you remember, this is just the vector partial f with respect to x, partial f with respect to y times partial f with respect to c, dot r prime of t, where r prime of t is x prime of t, comma y prime of t times c prime of t is 0. So in particular, this dot product holds when t equals t naught. So finally, we conclude therefore that grad f is perpendicular to uh, r prime of at t naught. So that means the vector grad f must be normal to this arbitrary curve that passes through P, which lies on S. Now, let's say we want to find the equation of the tangent plane at P, and the normal line, representation for the normal line at P. So where P is a point on the surface S. So to find those representations, we just need a vector perpendicular to the plane and a vector parallel to the line. So here we have this tangent plane. And this red line is the normal line. So from the theorem, the gradient of f will be normal to the plane or perpendicular to the plane at P. And this gradient is also parallel to the normal line at P. So let's say the gradient of f at P is ABC. Then the tangent plane can be represented by grad f that x minus x naught, y minus y naught, z minus z naught equal to 0. So in standard form, the equation of the plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. And for the normal line, we have this representation. So it's the vector x naught, y naught, z naught plus the scalar multiple of grad f, t times grad f, where t is in R. So So, equivalently, we have x naught plus 8t, y naught plus bt, z naught plus c times t, where t is in R, or t is a real number. Okay, so again, the equation of the tangent plane has this formula. It's just grad f that x minus x naught, y minus y naught times c minus c naught. And the normal line is has this vector representation. So vector x naught, y naught, z naught plus t times gradient of f. Apply the theorem on this example. So let's say the surface is given by xy cubed minus x squared times c plus yz squared equals 1. And point 2, negative 1, negative 3 is on the surface. Then we let f equal to this expression. Then grad f will be equal to this. This is easy to obtain since this is just a polynomial in x, y, z. Now, evaluating this gradient at the given point 2, negative 1, negative 3, then we get the normal to the surface at 2, negative 1, negative 3, which is 11, 5, 2. Therefore, the equation of the tangent plane is 11, which is the first component of the gradient, times x minus 2, plus 15 times y plus 1, plus 2 times z plus 3, equal to 0. And the normal line is represented by the vector 2 plus 11t, negative 1 plus 15t, minus 3 plus 2t. We have a similar result for functions of two variables. So let's say we have a curve C with equation f of xy equals k, where k is again a constant. Then the gradient of f evaluated at the point x naught, y naught is orthogonal to the curve C at the point x naught, y naught, where x naught, y naught must be a point on the curve. So let's apply this theorem to the following. So let's say we want to find the tangent line to the graph of the unit circle x squared plus y squared equals 1 at a given point. Then first we compute for the gradient of f at any point xy, and that is simply 2x comma 2y. Evaluating this at the point square root of 2 over 2, square root of 2 over 2, then we get the vector square root of 2 comma square root of 2. Since this vector is orthogonal to the curve or the circle at the given point, then the tangent line will have the equation square root of 2 x minus square root of 2 plus square root of 2 y minus square root of 2 over 2 equals 0. So you may or may not simplify this. And this is the circle, the tangent line. This point is square root of 2 over 2. And this is the gradient. So that concludes our discussion on directional derivatives, gradients, and tangent planes.